Okay, let's look at a little bit of a more planetary motion type thing. Let's say that we have two planets. One has a mass of m1, one has a mass of m2, one has a radius of r1, one has a radius of r2. The center-to-center distance between the planets is d, and somehow, magically, these two planets are maintaining a fixed distance between each other. Maybe they're co-rotating so that the center of mass is somewhere in here. It doesn't really matter. It's a little artificial. Our goal is to launch a projectile, maybe we'll call it little m, it's not going to matter, from the surface of one planet to the surface of the other planet with the minimum possible speed. I want to know what is the minimum launch speed that'll just barely get me to the other planet. I don't want to waste any energy that might be otherwise spent on something else. Now, we're going to, first of all, we're going to make an assumption, but it's not really an assumption, which is we're going to launch this projectile directly along the line that connects the centers of the two planets. And the reason why it's not really an assumption is because if you're trying to launch with minimal speed, if you launch at any other point or at any other angle, you're going to be spending some of your kinetic energy on angular momentum because you're going to be moving about the center of mass of this system. And we know that that's just going to require greater overall energy than launching with zero angular momentum. So if we launch it directly along this line that's connecting the two of them and, of course, their center of mass, then L equals 0. In other words, the angular momentum of your particle about the CM, or really about any point on that line, is 0, and hence we don't have to include that in our, rotational kinetic energy. So that's the first thing. It's definitely going to be something along this line. So we'll launch it straight up, if you will, when these centers are aligned. And next, what we're going to do is I'm not going to look at forces here. I'm going to look at an energy conservation argument. Clearly, there's going to be some point halfway, well, not halfway necessarily, but somewhere in between these 2 points where you're just barely going to make it over the potential hill before you start falling towards the other planet. So really what this is going to be is what speed is necessary to just barely get to that magical point with just barely 0 total speed. And that'll be the dividing line between making it and falling all the way back, not making it. So that means what I want to do here is I want to write down the potential energy of my little m as a function of position. So let's go ahead and put a little coordinate system on here. This will be the x coordinate where I've set the center at the center of the first planet for my x coordinate. And let's say I'm at some position here, x. I want to write down u of x, the potential energy as a function of x. Now, because we're dealing with non-uniform fields, I do have to use my full Newtonian gravitational potential energy. And as a reminder of what that looks like, usually write R here, we have a negative gm1 m2 over r, where m1 and m2 are not these m1 and m2, it's the two masses that are doing the interacting. So in this case, it'll be little m and m1, and I'll have a second term, which will be little m and m2. So I have to add the two potential energies of these objects. Okay, so let's look at the potential energy that this little mass has due to mass 1 on the left. So there'll be a minus sign. There's the g. The negative sign there is just to make sure these are attractive. We got Newton's constant g. I've got the mass of planet 1 and then the mass of my little projectile. And then I'm going to divide by the distance from the center of that mass to my position here, which in this case is literally just x. By the way, I've chosen my coordinates. The second term will also have a big G. It'll have an m2 and an m, but now I got to get this distance right. Okay, the distance from here to here is not x, it's actually d minus x. And I am subtracting it in that order to make sure the signs all kind of work out the way we want. Now the position of maximal potential energy is just going to be where the derivative of this with respect to x equals 0. So we can do that. I'll go ahead and pull out a negative g times little m from both terms because it's a constant between them. And then I've got m1 over x. Well, the derivative of that will be negative m1 over x squared. And remember, I pulled this minus sign out. So the derivative here is going to be m2 over the derivative of this. Well, there'll be a negative sign from this being to the negative 1 power. It's a quotient rule. But there'll be a second negative sign from the chain rule right there. So I'll actually end up with a positive sign here, m2 over d minus x quantity squared. And I want this to equal 0. Okay, so let's go ahead now and solve this for x. We'll need to move some stuff over and do a little cross multiplying, but it's not so bad. So doing that, we'll have what? m1 times d minus x squared equals m2x squared. I'll go ahead and take the square root of both sides. I don't have to turn this into a quadratic here. We know that d minus x is a positive number. I'm not interested in this thing going to the other side here. So x is less than d. So take the square root of both sides. I'm going to get positives. That's fine. And I'll have what? D minus x. And I'm actually going to move this m1 over here to get the square root of m2 over m1. I haven't really decided whether I'm using lowercase or capital M's here. Let's use capitals. These are planets. m2 over m1 under the square root times x. And then with very little extra effort, we can find this x. Maybe I'll call it x star or something to indicate it's the special point where the potential energy is maximized. And that'll be d over 1 plus this square root. Yeah. Okay, so there is the position of maximal potential energy. It does depend on the square root of these two masses. You might think, oh, you know, m2 over m1, shouldn't it be like symmetric between the two? Well, it kind of is if you were to go center things on m2 and measure this way, everything would turn out symmetrically. So even though it looks a little asymmetric, it's not going to matter. And now what I want to do is apply conservation of mechanical energy at this particular place. So what do we know? We know that the initial kinetic energy plus the initial potential energy, so my initial total energy, mechanical, has to equal the kinetic energy at this maximal point plus the potential energy at this maximal point. So wherever this maximal point is, energy is supposed to be conserved at both ends. We're assuming there are no external forces acting. It's moving under purely ballistic motion. Well, that's not so bad. K naught, my initial kinetic energy, is exactly the, well, 1/2 mv squared, I'm assuming non-relativistic, 1/2 m, little m, v naught squared that I'm looking for. There's the v naught. I am going to have to work this out, but my K star is 0. Kind of by assumption, right? The idea here is I'm trying to find the minimal V naught, and the minimal V naught is when it just barely makes it over the hill between these. If you go graph this function, there's asymptotes at x and d, but there will be a sort of central maximum. And if we want to just barely make it over that max, I'm expecting the kinetic energy there to just barely go to 0. And then u of x star, well, I'm just going to take this value and plug it in for the x's here and here. Okay, so let's try to write that out. I'm going to go ahead and take this result, move it over, and give ourselves some nice space for algebra. Okay, so continuing from where we left off, I want to write down my initial potential energy. Now notice, it's not 0. I do have potential energy even when we start with respect to both of these planets, so I have to write both terms. And they are both going to be negative. So I'm going to have this evaluated at x equals r1. This distance will be d minus r1. Okay, so that's everything we have for my initial energy. The final energy, I already told you we're going to put a 0 there right as it's making it over the hump. Now I'm going to plug in this x star to both of these and simplify. Okay, so as it is, doesn't look so bad, but unfortunately, these x stars are kind of messy. One thing we can do is we can just quickly go cancel all the little m's out of every term because it's not going to depend on our projectile mass. And let's keep in mind what we're trying to solve for here, which is this v naught squared. I won't bother taking the square root, you know, there'll be a big radical, but let's just leave it like this. there'll be a 2 that moves over. I'm going to move all these terms to the right, and I'm also going to factor out a big G because they're in all of these terms. So I'll have a 2 big G. And let's see what we're left with. So this term and this term will move over and become a M1 over R1, an M2 over D minus R1. R1. Here we'll have a minus M1 over X star, and here we'll have a minus M2 over D minus X star. Okay, it's not looking too bad. Now these two terms I really can't do much with. I'll leave them as is because they're all in terms of parameters that are already given, so there's no real simplification. However, the X star, because I have an actual value for that, we can do a little bit more simplifying here. There's a minus sign I'll factor out of both of these. And what do we have? We'll have, well, when I do this over this, I'll end up getting something flipping to the top. So let's write that as M1 over D, and then I'll have 1 plus this square root of M2 over M1. That's the first term. Plus, I pulled up the minus already. M2, now this one we got to be a little careful. D minus this. Maybe I will actually go ahead and write that out. So I'll pull out the D, but I'll write this as 1 over 1 minus 1 over 1 plus this square root. Okay, it's getting a little shaky here, but it turns out that this isn't as bad as it looks. When you find a common denominator here, I'll write that in blue or something. When I find a common denominator, I'll end up with a 1 plus this root minus 1 all over 1 plus this root. And this 1 and this minus 1 cancel. This is all in the denominator, so that 1 plus root, which is the same as this 1 plus root, will come up to the numerator. So it's not so bad. Okay, what can we do next? Well, we can see that both of these terms have this square root, and they also both have a D in them. So we can factor that a little bit. I'll go ahead and pull the 1 over D out to the front of everything. Okay, so look at this though. M2 over the square root of M2 over M1 is just going to be the square root of M1 times M2. And then we also have this 1 plus the square root of M2 over M1. Okay, finally, what I'm going to do is I'm going to FOIL these binomials out and see if they simplify a bit. Okay, so let's check it out. We've got an M1. M1 times this is going to be a square root of M1, M2. But then this square root of M1, M2 will be added to it, so there'll be 2 of those. And this times this, the M1s will cancel, and I'll have the square root of M2 times the square root of M2, which is just M2. Okay, so to finish things off, this thing is actually the square of binomial. It is root M1 plus root M2 quantity squared over D. That's kind of nice. It at least simplifies down a little bit here. Okay, now that is our final form for the minimum, at least squared, speed to go between these two planets. With this speed, you'll just barely make it over that hump located here before you fall towards the other planet. And then just to finish off where the inspiration of this came from, where did this actually come from? I can't even remember. I think it came from a Physics Today challenge problem or something. They didn't give it in this general form. Let's specialize now to the case where D happens to equal 4R and R1 and R2 are both the same radius and M1 and M2 are both the same mass. So let's look at that particular case. If we plug in those special values, so two identical planets whose distance is separated by 4r, we can see that we're going to get what? M over r, m over 3r, and then, well, 2 of these squared. Again, the d will be a, what was it, a 4r. And at the end of the day, you'll get a 3gm over 2r as your final answer in this sort of red special case. The problem is a little easier symbolically when you assume all this symmetry. That's how things usually work out, but it's not that much harder to generalize, and it's kind of fun to see how this might work in a more general setting. All right, so there it is. That is our minimum speed to just barely make it from the surface of one planet to the surface of another planet, provided there's no motion along the radii between them. QED.